So let's start now going through the details of the 7 addition reactions that we talked about. By talking about addition of alcohols to form acetals. And this is a particularly important reaction because I absolutely guarantee that you're going to be called upon to write the mechanism for acetal formation or the mechanism for acetal hydrolysis, since this is an equilibrium reaction at some point. And to keep things simple, we're going to start with ethanol as our aldehyde, the simplest aldehyde, except for formaldehyde, of course. And we may as well use a simple alcohol. So we're going to use methanol as our solvent. It's also going to be the reagent. And then concentrated HCl as the catalyst. And you recall that concentrated HCl is 37% HCl by mass, or approximately 12 molar hydrochloric acid, roughly. So the first thing that's going to happen is HCl is going to protonate the methanol. HCl is a strong acid in water. Methanol is very similar to water, so HCl is a strong acid in methanol as well. So what we will have in solution is the methyloxonium ion, chloride ion, which is a spectator throughout this process. And methanol, right? So just as in hydration, we have a combination of hydronium ion and water. In this acid catalyzed addition of alcohols, we have a combination of methyloxonium ion and methanol. This reaction can also occur as far as the hemiacetal in basic ethanol. So if instead of adding concentrated HCl as a catalyst, we were to add some NaOH, the NaOH would deprotonate the methanol to give us some methoxide ion in solution. Sodium ion in this case would be a spectator, and we have a mixture of methoxide ion and methanol that can also add across that carbonyl group. But we can only go as far as the full acetal, where we have the 2 OR groups attached in the presence of acid. In the presence of base, we can't go any further than the hemiana now. So we can immediately start thinking about what's likely to happen if we put a carbonyl group in the presence of methanol and methyloxonium. Logically, since we're in acid, we're going to want positively charged intermediates. The first step is going to be to protonate carbonyl oxygen. It's an equilibrium step to generate a resonance stabilized carbocatide. So step 1 is to protonate carbonyl oxygen. And you will find that that's step 1 in almost every acid catalyzed mechanism. Not every one. In the case of imine formation, the first step will actually be nucleophilic attack because of the greater nucleophilicity and basicity of the nitrogen atom. But in most cases, when you're in an acid catalyzed solution, protonating the carbonyl oxygen is a logical first step. Now that we have a positively charged carbon that can be readily attacked by the oxygen lone pair, this is the equivalent of the reaction with water, except that we have large quantities of methanol and only very small quantities of water, so methanol is carbonyl carbon. Which will generate a positively charged intermediate, a proton transfer step. Base reaction will regenerate the acid catalyst and generate the heavy M now. So the net reaction is to add the elements of methanol across the carbon oxygen double bond. This mechanism is absolutely identical to the mechanism of hydrate formation under acid catalysis. Protonate the carbonyl oxygen, attack the carbonyl carbon with the nucleophilic oxygen, and then do a proton transfer. The only difference is the identity of the nucleophile is now a methanol. Under basic conditions, it would follow the same pathway that hydration forms under basic conditions. The methoxide ion would attack the carbonyl carbon, generate an alkoxide ion, and then that alkoxide ion can undergo proton transfer reaction to regenerate the methoxide. Once again, that's identical to the mechanism of base catalyzed hydration. We have nucleophilic attack on the carbonyl carbon, followed by protonation of the alkoxide ion. And as always, you can see that the acid catalyzed reaction requires more steps than the base catalyzed reaction. It's an additional proton transfer, 2 proton transfer steps in the acid catalyzed mechanism, just 1 proton transfer step in the base catalyzed mechanism. You can see that under the acid catalysis, our intermediates are positively charged, our starting material product are neutral. Under base catalysis, our intermediate is negatively charged, and our starting material product are neutral. Acid catalyzed reactions, you want positively charged or neutral intermediates. Base catalyzed reactions, you want negatively charged or neutral intermediates. This is as far as you can go under base catalysis. It's not possible for the oxide ion to come in here and do an SN2 displacement of hydroxide, because hydroxide is not an effective leaving group in a nucleophilic alkyl substitution. The reaction is readily reversible. Methoxide can simply take this hydrogen off the acidic alcohol, regenerating the alkoxide ion, and then this can come back down and kick off the methoxide. Top reaction is also readily reversible. You could protonate the OCH3 group, lose methanol as a leaving group, and then deprotonate the carbonyl oxygen. So under base catalysis, the hemiacetal is as far as it goes. But under acid catalysis, it's possible for this reaction to proceed the rest of the way. If we reversed step 3, we would protonate this oxygen of the OCH3 group. But there's no difference in basicity between the 2 oxygens. So it's equally possible for the acid catalyst to protonate the oxygen of the alcohol. So step 4, 4 would be protonate, alcohol, or the hydroxy group, I guess I should say. This isn't really an alcohol. Though it's not possible for hydroxide to leave as a leaving group in a nucleophilic alkyl substitution, it's quite possible for water. Water is a neutral leaving group to leave. So we can lose water. That will generate a resonance stabilized carbocation that looks a lot like this other resonance stabilized carbocation, with the exception that there's not a hydrogen on the oxygen, now there's a methyl group. Which means that we can't go backwards the equivalent of step 1, because the methyl group isn't going to fall off as CH3+. The primary carbocation or the methyl carbocation is not very stable. The carbocation can, however, be attacked by methanol, just as the other carbocation was. So we have a second nucleophilic attack. With a second OCH3 group on there. And then we're just one proton transfer away from the full acetal. So methanol can come in, take that hydrogen off, to generate a neutral product. Added 2 molecules of methanol to the carbonyl-carbon, and once again regenerating the acetals. So overall, this is a 7-step mechanism with 4 proton transfers. Step 1 is a proton transfer, protein and carbonyl oxygen. Step 2 is a nucleophilic attack. Step 3 is a proton transfer to take that proton back off. Step 4 is a proton transfer. So the net effect of steps 3 and step 4 is simply to switch the proton from being attached to the OCH3 group to being attached to the OH group. We then have the loss of the leaving group, followed by our second nucleophilic attack and our final proton transfer step. So step 1 and step 4 are protonations, where we add a proton, whereas steps 3 and step 7 are deprotonations, where we remove the proton. We've got the 1 loss of leaving group, and we've got 2 nucleophilic attacks. Step 2 and step 6 being nucleophilic attacks. This reaction is readily reversible. Just retrace the steps, and the principle of microscopic reversibility applies here in that the reverse reaction will go through exactly the same set of intermediates as the forward reaction. So we will start by protonating one of these methoxy groups. We'll then lose methanol as a leaving group to form a resonance stabilized carbocation. Water will attack as a nucleophile, and I'll go through that mechanism in a subsequent video. So this 7-step mechanism in one direction or the other direction will guarantee